So, welcome to this next lecture. Let me continue from where I left off. So, let me close this integral here. So, we look at this part here. So, what I have is real integral minus infinity to infinity, integral minus infinity to infinity e to the power of minus I k x x minus x1 e to the power of, or let me not use so many, minus I k y y minus y1 dkx dky. That is the part, second part. Okay. So, here we make some substitutions, which is what I say. So, this is the substitution. Kx is equal to kb cos theta, ky is equal to, or kp, sorry, please take it as the same, b for beam, p for plate, but kp and kb are same, but I will correct it, kp. Okay. Occasionally I may write this kp as kb, but though for me both are same. So, kp sin theta, okay, and x minus x1 is sum r cos alpha and y minus y1 is sum r sin alpha. So, if we do this, we get real part integral minus infinity to infinity minus infinity to infinity e to the power minus I k b cos theta r cos alpha minus I k b sin theta r sin alpha dkx dky. Okay, or it is the real of, let me shorten this notation, both going from minus infinity to infinity, e to the power of minus I k b or kp, again I have the same problem, kp r cos of theta minus alpha dkx dky. Then, so now what we will do is we will convert from rectangular to polar. Okay. So, my dkx, so what do I have here? I have kx is equal to kp cos theta, then I have ky is equal to kp sin theta. So, I have dkx given by cos theta dkb minus, again I am going back, okay, kp sin theta d theta. Similarly, dky is given by sin theta dkp plus kp cos theta d theta. Okay. If I put it in a matrix form, I have dkx, dky is equal to cos theta minus kb sin theta kb cos theta dkb d theta. So this is the matrix where the Jacobian comes from. So I get the determinant as kb cos square theta plus kb sin square theta, which is dkb, which is kb, kp, okay. So if I change the integral from rectangular to polar, okay, so what I will get is the real part of integral 0 to infinity integral 0 to twice pi e to the power of minus I k p r cos theta minus alpha kp d kp d theta divided by square root of k a square minus k p square. Okay. Now I'll give you a result here, which is integral 0 to twice pi e to the power of I k rho cos psi d psi is equal to twice pi j0 of k rho, okay, where j0 is what? The Bessel function, first kind, 0th order, okay, oscillating decaying sinusoid, okay. So now the full integral becomes rho a c k a divided by 8 pi square double integral over the surface 0 to a 0 to b 0 to a 0 to b v x comma y v x1 y1 dx dy dx1 dy1, then the real part of integral 0 to infinity twice pi j0 kp of r kp dkp divided by, what I mean is that here, divided by square root of k a square minus k p square. Now this integral will remain real only as long as kp is less than or equal to ka. Okay, if kp exceeds ka, this becomes imaginary. So what I will do is this removal of this real, and the integral limits change from 0 to ka. Okay. So now if I use this to p and do some cancellation here, then I can write rho a c k a by 4 pi integral s v of x comma y v of x1 y1 dx dy dx1 dy1 integral now 0 to ka, okay, then j0 kpr kp dkp by square root of ka square minus kp square. Okay. So, I will use another result now, which is, okay, just a result from integral tables 0 to k j0 or z dz by k square root of k square minus z square is equal to sin kr by kr. We will use this result. Okay. So, we will use this result here. Okay. So, now what happens? What that does is we get this power integral. We are continuing with that PW rho a c ka squared, see the squared coming in, that is because of the extra k in the relation we have used. So, this is s x v x comma y v x1 y1 dx dy dx1 dy1 sin kar over kar. Okay. So, this extra ka is why this becomes ka square. Okay. So, we reached one more stage. Now, we have sin kar by kar is written as, if you recall the R definition, sin ka square root of x minus x1 whole squared plus y minus y1 whole squared divided by ka square root of x minus x1 squared plus y minus y1 squared. Okay. So, how do we use this? See, Majdanik's main idea here at this stage was to separate the x minus x1 type term from y minus y1 type term. They are both of them caught up under this square root. Okay. He wanted to separate the two. So, how does it happen? We have a very nice relation, sin ka square root of x minus x1 square plus y minus y1 squared by ka square root of x minus x1 squared plus y minus y1 squared given by this relation 0 to 1. Okay. cos beta Ka x minus x1 J0 alpha Ka y minus y1 into alpha by square root 1 minus alpha square d alpha. Alpha and beta are arbitrary numbers. Alpha square plus beta square is equal to 1. Okay, the 0 to 1. Okay, so now this is going to be replaced. This is going to be replaced by this. Why is that? Because this is a simply supported plate, so x function and y are separated. However, it becomes a problem here because x minus x1 and y minus y1 are peculiarly related here. But you can see if I replace this with this, x minus x1 and y minus y1 become separate and outside of the square root. Okay, so that's a great advantage. So now what we do is we use that, we use this new relation. These are very lengthy, so I need more and more horizontal space. So let's see, I will denote my one constant E as rho A C K A squared, okay, by B0 squared, the amplitude by 4 pi, that is my E, okay, just to shorten the presentation. Okay, so now what happens, my power integral, let me see if I can fit in one line, E integral 0 to 1 integral over area once, area twice, then sine m pi x by a sine n pi y by b. Okay, let me write it below here, it's in line, but sine n pi y m pi x1 by a sine n pi y1 by b in product. Okay, this will go and sit here, further into cos of beta Ka x minus x1, okay, dx dx1 dy dy1 and further J0 alpha Ka into y minus y1 alpha d alpha by square root of 1 minus alpha square. Okay, so they are all in one line. This term will come up here, this term will come up here, they are all in one line, one integral. Okay, now we see that x comes here, x1 comes here, so I have dx dx1, then I have x minus x1 coming here. So we will just look at the x and x1 integrals. Okay, so this S is a surface area integral, so 0 to a 0 to b, same here. So out of that we are looking at the 0 to a twice. So we have 0 to a sine m pi x by a integral 0 to a sine m pi x1 by a, okay, then cos beta k a cos beta k a x minus x1 dx dx1. ठीक है, so we get integral 0 to a sin m pi x by a, integral 0 to a sin m pi x1 by a, and e to the power j beta k a x e to the power of minus j beta k a x1 plus e to the power of minus j beta k a x e to the power of j beta k a x1 by 2 dx dx1. Okay, so this is now simple enough. So you will get two terms. Okay, you will get a half integral 0 to a sin m pi x over a into e to the power j beta k a x dx into 0 to a sin m pi x1 by a e to the power of minus j beta k a x1 dx1. So that is this part, and similarly this multiplied by this part, and they are the same. So you will get a doubling. Okay, if you carry out this integral, okay, so carry out, what do you get? You will get 4. I am not now giving all the details, it can be done by hand or maple, doesn't matter. A square, okay, divided by m square pi square by a square minus beta square k a square whole squared, okay, into either cos squared of or sine squared of what? A beta k a by 2. Okay, this is in the denominator, this is in the numerator. So cos you use when m is odd, you use cos, you use sine when m is even. It's simple. Okay, so within this 0 to 1 integral we have done the x part of the whole integral, it's done. Okay, so this will now come only under 0 to 1 integral, there is no y in here. Okay, so let's see. So how does the whole integral look, for example? So let me see, p of omega is equal to the constant e in front, integral 0 to 1 4 m square pi square by a squared cos squared or sin squared of what argument? A beta Ka by 2, that is the argument for both. It's either or, cos when m is odd, sin when m is even, divided by m square pi square by a square minus beta square Ka square whole square. Okay. Further, integral now, only the b integrals remaining, right? Sin n pi y by b, sin n pi y1 by b, j0 alpha Ka y minus y1 alpha d alpha by square root of 1 minus alpha square dy dy1. Okay. So one more result we use. What is that? The result to be used is this: j0 alpha Ka y minus y1 is equal to 1 by twice pi integral minus pi to pi e to the power I alpha Ka y minus y1 sin theta. This is 1 d theta. Okay. So we'll include this. So what happens to our result? We have this 1 by 2 pi coming in. So e by 2 pi, okay, integral 0 to 1 4 m square pi square by a squared. So either cos squared or sin squared of what? A beta Ka by 2 divided by m square pi square by a square minus beta square Ka squared whole squared. Okay. Now an extra integral has come in. Okay, minus pi to pi. Okay, integral 0 to b, integral 0 to b sin n pi y by b sin n pi y1 by b e to the power I alpha Ka y minus y1 sin theta divided by square root of 1 minus alpha squared alpha d alpha dy d, hold on, dy dy1 d theta alpha d alpha. Okay, alpha relates to this integral, so please don't forget. Okay, and remember alpha square plus beta square is equal to 1. Okay. Now, okay, so we look at this integral. The time is running out. Let me stop here. We'll continue. Okay, thanks.